All right, we're going to do a couple more example problems here involving gravity and free falling objects. And so this next question says that Daredevil Dave wants to break the world record for the fastest free fall dive of 380 meters per second. And we're asked to consider how long he would have to fall to achieve this speed. So we're going to assume that Daredevil Dave, he's a skydiver. He's going to jump out of a plane or something like this, and then fall freely. We're going to assume that there's no air resistance here to slow his descent, and that he's just going to continue to accelerate due to gravity as he falls faster and faster, and ultimately trying to reach this speed of 380 meters per second. So let's write down what we know. We're going to start with that final velocity that Dave is after. Dave wants to achieve a final velocity of 380 meters per second. So that's going to be our final velocity. And what else do we know? What else do we know? We know that if he's skydiving, if he falls from a plane or jumps from a plane, we're going to assume that as he jumps or falls, he's not giving himself any initial velocity. He's just going to step out of the plane and fall with an initial velocity of zero velocity. So again, that's important to always consider. As your falling object, is it starting with zero velocity as it's being dropped? And oftentimes we'll see situations that involve that. All right, the last thing we know is that as Dave falls, he's going to accelerate. As falling objects do, they're going to accelerate with an acceleration of 10 meters per second squared. And then one thing we want to probably establish here also is that his acceleration is going to be negative if we call that downward direction, again, the negative direction. Then he's going to be falling with negative velocity as he falls, which means that this final velocity that he's after needs to be a negative velocity. He needs to be falling downward. He's not going to jump from the plane and fall upward. Instead, he'll be falling in that downward negative direction. All right, so let's take a look at the kinematic equations here that we have to work with. Again, these are the three kinematic equations that help describe motion and how motion changes and the different features of motion. We've got the final velocity that we've been given. We know the initial velocity. We know the acceleration. And we're looking for the time here. We're asked to figure out how long is Dave going to have to fall for in order to reach that speed. So the equation we want to pick here is the one that incorporates all four of these. And again, it's this first kinematic equation. Final velocity is equal to initial velocity plus acceleration times time. All right, but the problem is this equation is not written in the form that we need it to be. It's not written in terms of time. It's written in terms of final velocity. So we're going to have to do a little algebra to rearrange our equation. All right, so let's start with the equation as it's written on the formula sheet. And let's think about the steps that it would take to get the time variable here isolated. How do we get time all by itself on one side of the equal sign? Well, as we look at time, we notice that it's in this term along with the acceleration, and that term is being added to our initial velocity. Now, if you want, you can just say, well, the initial velocity is 0, so this first term really doesn't matter. We can cancel it out since it doesn't equal anything. It's just 0. And so at this point, our equation is really just final velocity is going to be equal to acceleration times time. And now it's one pretty easy step to get time isolated. We're just going to divide both sides by the acceleration. And in doing so, we can cancel the acceleration on the right side, leaving us with time as our variable that we're after, isolated. And so we can express time in terms of the final velocity divided by the acceleration. All right, so how long is it going to take Dave to reach that speed? We can plug our values in for final velocity. Negative 380 meters per second. That's the speed he wants to achieve. He's going to be allowed to accelerate at about 10 meters per second for every second that he falls. And so we'll find that time is going to be about 38 seconds. 38 seconds to break a world record. Sounds doable. Let's try another one. All right, on Earth, it only takes about 3 seconds for a falling object to reach a speed of 30 meters per second. On Mars, it takes 8 seconds. What's the acceleration due to gravity on Mars? All right, so Mars is a different planet, and so due to its mass and also other factors about Mars, it's going to have a different rate at which things fall due to its gravity. All right, so the information that we're given here, we need to pick through it and think about, well, what's important? What do we need to know in order to find the acceleration on Mars? Okay, well, if we're dropping an object, we can again assume that the initial velocity is 0. And we know that on Earth it takes 3 seconds for an object to reach that final speed of 30 meters per second, but for Mars it's going to take 8 seconds. All right, so it's going to take a time of 8 seconds on Mars to reach a final velocity of 30 meters per second. And we're not really concerned about the 3 seconds here for time because that's the time it takes to reach that speed on Earth. We are more concerned about the acceleration due to gravity on Mars. So let's just call this A, and then I'm going to put a subscript here, Mars. Okay, we're looking for the acceleration on Mars. All right, we know the initial velocity is going to be 0 because we're dropping this object. We're going to let it fall for 8 seconds because that's how long it takes to hit the ground on Mars. Or not to hit the ground, but to reach a speed of 30 meters per second, the final velocity. So let's find out what the acceleration must be on Mars and compare that to what it is here on Earth. All right, so again, the equation we need to use is the same one. It's equation number 4. This time we're looking for A, the acceleration, given the time and given the initial and final velocities. All right, so let's rearrange the equation and get it in terms of acceleration. Vf equals Vi plus A times t. All right, like before, our initial velocity is 0, so we can just cancel out that first term. We don't have a value to plug in for Vi, so the final velocity is just the product of acceleration times time. To isolate the acceleration variable, we simply divide both sides by time. The times cancel on the right. And we see that the acceleration will be equal to final velocity divided by time. Acceleration equals final velocity divided by time. All right, so let's substitute our values in that we were given in the problem and find out how fast things accelerate on Mars compared to Earth. All right, the final velocity was 30 meters per second. And again, because things are falling just like they would here on Earth, falling downward, we might go ahead and establish that downward direction as being the negative direction. And if that's the case, then we do need to put a negative sign in front of this final velocity here to indicate that that's an object that's falling at that speed in the downward direction. All right, so negative 30 meters per second as it falls downward with that speed. And it's gonna fall for 8 seconds. That's the time. And so 30 divided by 8, we can calculate that. 30 divided by 8 comes out to a decimal. 3.75. And again, that's the rate at which things speed up as they fall on Mars. That's the acceleration due to gravity on Mars. So that's going to be meters per second squared. And it's negative. It's downward just like it is on Earth. But how does that compare? Remember, Earth's gravity accelerates objects at about 10 meters per second every second that they fall. On Mars, it only accelerates objects at about 3.75, 3 3/4 of a meter per second every second. So it's a little bit more than a third of what the acceleration is on Earth. So what does that mean? It means it's going to take things a lot longer to fall. Like we saw, 8 seconds instead of 3 seconds If you were to jump on Mars, it'd probably be a little easier to jump. You might be able to jump higher on Mars than you could on Earth because that gravitational influence, is not nearly as strong as it is here on Earth. All right, so that's another look at a couple problems that involve kinematic equation number 4 and how we would use those to solve problems that deal with falling objects.